Okay, so we were discussing about Hcp system and their slip systems. So we started with looking at how to give indices to their planes and direction, then I showed you some examples, and then I listed out some of the possible slip systems in Hcp. One of the things that I want to add to the slip systems that we discussed here is how many independent system each of them is. So, here if you look at it, it is 0 0 0 1 plane. So, it is only one plane, it is not a family of plane and one direction. This direction, the 3 possible directions, but then if you look at independent systems, there are only 2 independent systems. So, we are talking about so, for the basal plane we have only 2, similarly for prismatic we get only 2, and pyramidal and basal pyramidal together they give 4. This is for the A type of Berger vector slip system. The other one we talked about was the C plus A system, and over there if you look you will have another few sets of possible slip systems. So, here you have the 4 slip systems over here for the 3 planes over here, and so there are quite a bit of possible slip systems that are available in Hcp system. However, not all of them are active at all the times, and if you look at the Pearl-Navarro stress relation, then you would find that only the basal slip system is the most preferred one. Why? Because if you go from there, we know that the planes which are furthest apart, they should be the most, they should give you the lowest shear stress, the critical resolved shear stress. And for the Hcp, although in the third direction C, there is no direct relation between C and A, as you will see that if it is ideal case, what we will explain what is ideal case, then in the ideal case the plane systems are far apart, and when those planes are further than the ideal system, then again the basal slip becomes much more preferred. But before that, there is one more thing that I want to let you know, that there is still another type of slip system theoretically possible, where you have only C type of Berger vector, but unfortunately this does not exist on any plane. So, you will write it as like this, and this there is no independent slip system, meaning this does not exist. So, theoretically it is there, but practically we do not see anything like this. Now, the next thing is, like I said, what is the ideal hexagonal system? Like I said that you remember in the beginning I said that in the Hcp it is not really hexagon, the unit cell is not hexagon, it is rhombus. We have atoms over here, and these are the basal planes, but in between also there is one layer and there is atom over there too. So, if you draw a middle level mid plane somewhere over here, which is this mid plane will be called the B type of layer. So, these are your A layer and this is your B layer, and in this B layer somewhere over here in only, so if you divide it, there will be 2 triangles and one of these triangles will contain this B atom. So, this forms B layer, and these layers form AB. And we all know, and I have already said again and again, that HCP is AB type of packing. Okay, so now coming back to this, now let us look at these 4 atoms 1, 2, 3, 4. Now, if you look at it, this is at the centroid of the triangle over here. So, this when you connect, what this forms is a tetrahedron. And you can clearly see that all of them are equilateral triangle, and therefore, if this is A, all of this length would be A. So, it is a tetrahedron with edge length equal to A. And again let me remind you, this is when we are talking about ideal. Okay. Now, in non-ideal case, this is your C direction and this is your A direction. There is no relation, there is no way to exactly define what should be the relation between C and A. What we are looking at right now is C by A ratio when it is an ideal condition. So, trying to find C by A for ideal So, if you look at it, this height which will be equal to C by 2 you can very easily show that this is equal to root 2 by 3 times A, which is nothing but half of C. So, this is equal to C by 2, which implies that C by A ideal is now this whatever we are describing as ideal is also a close packed structure. Meaning packing fraction is equal to 0.74. So, only when you have an ideal system like this, you will have the highest possible packing fraction of 0.74. So, this is also that, and in that case it will be called a hexagonal close packed structure. Which is HCP. Now, let us remind us what the Pearl-Navarro stress was. Pearl-Navarro stress is given by this equation. Where B is the if we write in plane spacing, then this will become A. So, W is A by 1 minus nu. So, A becomes planar spacing. So, if you want tau Pn to be small, what do we want with A? A should be large. So, you can see if A is large, this being a negative quantity, tau Pn will be small. So, A should be large, and this happens for basal plane. So, this is basal plane assuming ideal condition, ideal HCP. Now, if the A, and let me call it now AI. So, basal plane Now, if A for any HCP which is not an ideal system, A is greater than A ideal, then it means that the planar spacing is larger than what we are expecting. In that case, basal plane, basal slip more preferred. And as you keep reducing A, so if you go less than A, basal slip will, the spacing between basal slip will not be as large as we wanted, and some of the other spacing between some other planes, for example, the prismatic planes may become larger, and therefore, those may start to become the dominating shear stress, or they will be the more preferred slip plane. So, basal slip not as much preferred, and we will look at the values of shear stress, but right now let me show you what it does to the, when the C by A value changes, how our different planes become preferred. So, let us look at so here I will put C by A ratio, and remember the ideal value is 1.66, and very few metals actually show this ideal ratio, and here I will be putting tau CRSS value for different slip systems. So, one of them is the basal, which is what we are most interested in, because we said this is what is the preferred system for an ideal system, for an ideal HCP or the closed packed structure, or when the C by A ratio is greater than the ideal value. Then we will look at prismatic, which is the second most preferred one. Then pyramidal, and the C plus A type. Okay, so let us list out some of the elements. Metals, cadmium is one of the hexagonal system, zinc is another one, magnesium is another one, zirconium is another one, titanium is another one, and beryllium is another one. This is not the exhaustive list, but we are just comparing here some of these values. So, what are the C by A values? And as you will see, I have put it in a descending order, and these values have been taken from the book by Hull and Bacon, and some other values are also taken from the book by Wei Chai and William D. Nix, which are given in your references. If you look at the course handout over there, they are mentioned as references. So, if you look at this, we see that in this particular list only magnesium comes closest to it, 1.633, and the elements on the above it have C by A ratio higher than 1.633, and below this have C by A ratio lower than 1.633, which we said is the ideal ratio. So, now when it is higher, then what would we expect, that the tau CRSS for basal slip is very small, or the smallest, and it does so happens it is less than 0.1, and all these values are in megapascal. Even zinc is less than 0.1 megapascal, and if you go to magnesium, it is a little bit higher, but is still in the same range. When we go to zirconium, it is much higher than all these, 3.5, and titanium is 3.1. Now, here are some you can say discrepancies, because 3.1 is the calculated value and the measured value are actually much higher 80, but we are just putting some values which are falling in the trend, but you should remember that there will also be 80 which is the experimental value, and this is beryllium which is 5. So, clearly you can see that as the planar spacing of the abyssal planes is decreasing, the tau CRSS values are increasing, meaning it is no more as easy a slip system or as easy a glide plane. Now, let us look at some of the other ones. Now, here all these data are not available. So, we will put only the data we have. Again, most of these values are from two books which I mentioned earlier. So, what do we see here? That the prismatic slip tau CRSS for the prismatic slip keeps coming down, or at least that is the trend from whatever values we have 40, 21, 12, and over here also pyramidal values, here the ratio was very high 0.1 to 7, but here the ratio is much lower 3.1 to 4.2. So, even the pyramidal slips are becoming a little bit more easy as we go from C by A ratio very high to very low. Okay, so that is the slip system preference based on the tau Pn values. Now, let us look at what are the possible Berger vectors. So, we have seen C and A, but those are only when we have the full dislocation, but there is also a possibility of partial dislocations as we would see, which is similar to what you see in a FCC system. And not only that, similarity to FCC does not end over there. In FCC, if you remember, we talked about Thomson's tetrahedron, which give you all the possible slip planes, partial dislocation, Berger vector and so on. And here also you have something called a bipyramidal system, which is able to describe all the possible Berger vectors, not the slip planes, but all the possible Berger vectors. So, let us first see where does that come from. So, again I will have to draw the hexagon . And now let me put atoms . And you remember there is an atom also at the center here. And what else this is not all of it, you remember I said that there are 3 more, there is another layer in between, 3 more atoms. So, the way we will place it, this will, if you make a triangle over here, then there will be 6 triangles, out of which if you look at it, 3 of those triangles, alternate triangles will contain those atoms. So, let us say one of them is over here in between this one. So, this is one atom over here. Now, if this is the one that is already covered, then we should have another one over here. So, let us have another atom over here, and that means the third one will have to lie over here. So, these are the 3 atoms over here. Okay, so, now let us call this as point A, this as point B, and this as C, and let us call this the atom over here as S. So, now we will be able to make you can say single pyramid. Now, it is not a tetrahedron because not all the sides it is not 60 degrees. So, we will draw something which will look like this. So, we will say A. So, this is A, this is B and this point is C, and over here we will draw some, it is at the centroid. So, from centroid we will connect all these. So, this becomes S. So, this is one half of the pyramid, but now that is not the complete picture when we want to describe all the Berger vectors, because this is not at 60 degrees, this line is not same as this line, these are different, and therefore, we will have to describe it separately. So, here comes another pyramid which goes below it, and it looks like and here we will call it T. So, now we have A, B, C and on one side we have S, other side we have T, and when you connect S and T, it intersects at a point which we will call sigma. Now, all these points will become important when we try to describe the various possible Berger vectors. So, let me also draw. So, ABC, if you look at it, that will be a equilateral triangle. So, ABC will look like this. We are looking from the top, perhaps something like from the S, and therefore, this S and T, they will fall at the centroid of this equilateral triangle. So, S, sigma and T, if you are looking in a projection view, all of them lie at one point. So, let me use a different color. So, this is the projection view. Just to make the picture more clear, I have put it like this. So, what do we get from this, all this construction in HCP? That is the useful thing, that we can now write what are the Berger vectors in terms of this, and we know with respect to this drawing with respect to the hexagon that we have over here. So, now let me write the Berger vectors and there is a category. So, this is first let me write for perfect dislocations. Now, even in perfect dislocations, you would see that there is not only one possibility, there are more than one possibility which we have already seen, and now we will write in terms of these alphabets. And their negatives. So, that becomes so, although there is 3, but when we add negatives it becomes 6. Then the other category is, okay, let me ST and TS. This is ST and the inverse is TS, which is the C type of Berger vector, that is also one full Berger vector for a full dislocation. Then there is something called as SA/TB, which is something you can say from the center of ST to the center of AB, that kind of vector is called ST/AB. And since there are so many possibilities, SA, SB, SC, TA, TB, TC and then AB, BC, CA. So, it will intersect all of those, and therefore, you will get, including their negatives, you will get 12 possible Berger vectors. So, these are the perfect dislocations. Now, let us look at the possible partial dislocations. So, how do we, so here in brief what we are doing is we are connecting all the endpoints A, B, B, C, C, A, S, T, T, S, and when you, for the SATV you take the, again you take the full vector over here and the TB, both of them are full vector, and you connect them, what you get is a vector called as SA/TB. So, all of these are connecting endpoints, but when we are talking about partial dislocations, one way or the other they will be connected with sigma. So, what are those? First you can connect only the A's. So, this will become AB, sorry, A sigma, B sigma, C sigma, and then negative, which means sigma A, sigma B, sigma C. So, this is 6. Now, this can also be connected to S and T. So, it is S sigma, T sigma, and the negative, which is sigma S, sigma T. So, this is another 4 Berger vectors, and other than that you can also get Berger vectors. So, this is also connecting endpoints, but this is, as you can see, this is not a full vector. AS, BS, CS, then AT, BT, CT, and the negatives. So, it will become SA, SB, SC, TA, TB, TC. So, these are 12 Berger vectors. So, you see all the possible Berger vectors that are there in HCP can be listed using this bipyramidal structure. And the similarity with FCC does not end here, as we will see that even the dissociation into partial dislocations do happen, and you can draw the cartoon similar to what we have in the FCC system. Now that we have mentioned the Berger vector here, so it is also imperative that we compare their magnitude and their energy vectors. So, let me put a comparison of various vector magnitudes and their energy, because energies are what will tell us which one is more preferred. And as you will see clearly that A vector is, when you are talking about a perfect dislocation, we have, like I have said, that basal slip is preferred, and therefore, in the basal slip you have the A vector, Berger vector, and that will have the smallest energy. So, that is something we are expecting. Now, let us see if it actually comes out like that. So, let me write the type, and over here we have comparing first the vector, then the magnitude, and then their energy. So, type, when I say, it can be AB type. So, you can see in the previous one that there are 6 different types, 1, 2, 3, 4, 5, 6, 7, actually 7 different types. So, we will compare all these 7. AB type, which is 1/3, 1 bar 20. Then we have the TS type, which is the C vector. Then we have the SATB type, so this is what we, in other words, what we were describing as C plus A vector. This is what this is represented as SATB. And then comes the partials, A sigma type, and right now I have not told you what should be the Berger vector, but here I am writing directly, and next will come when we talk about the partials, then you will see this form. But then I have also showed you the pyramid, and from the pyramid you can directly find out that this is what the vector would indeed be. So, these are the partials. On the left hand side we have the full dislocations. So, now let me so as I have already given you the vectors, this is just the form of a vector, and this is, like I said, from the bipyramid you would be able to directly get these vectors, and we have listed all the possible different perfect dislocations and partial dislocations. Now, what is the magnitude? We know this is nothing but A. So, the magnitude of this one is A. What is this magnitude? This is C, but here for the sake of comparison we will want to convert all of these to A. So, what we will do is we will assume an ideal Hcp system. So, assume ideal Hcp system where C is equal to root 8 by 3 A. So, this automatically means that C is we want to compare in terms of A. So, this becomes root 8 by 3 A. Now, this is C plus A. So, will actually it is not really C plus A, as you would see, this is C square plus A square over 1 by 2, and this will, if you look at it, it will come to root 11 by 3 times A. Now, what is this? This is a partial Berger vector, and this is nothing but A by root 3. This is again a partial Berger vector, which is half of the C vector is equal to C by 2, and therefore, you can write it as root 2 by 3 A. And this last one is not so easy to come or derive it, but you will have to take my word for this, that this is A square by 3 plus C square by 4 1 by 2. Now, let us compare their energies. So, for energy we know, and we are not talking in terms of absolute values, we are only comparing the relative values. So, what we do is just take the square of the magnitude of the Berger vector. So, whatever we obtained here we multiply, we square it. So, this becomes A square, this becomes 8 by 3 A square, this becomes 11 by 3 A square. So, this is for the perfect dislocations. Now, we have the partial dislocations, A square by 3, this is 2 by 3 A square, and this is A square. So, first few things to note over here, that when you are talking about perfect dislocations, AB has smallest energy, AB type vector, not just the AB, has smallest energy. You can see these are much higher than that. Now, when we are talking about the partial dislocations, which has the smallest energy, you can see that this one A sigma type vectors are the smallest. So, we have perfect dislocations and partial dislocations, and another very interesting thing is that your AS type partial dislocation, this one as you can see has similar energy as that of a full dislocation, has same energy as AB type full dislocation. Okay, so, this is clearly AB types dislocation are much preferred when we are talking only about the partial dislocations, but even now here we move on to the next part, which is about dissociation of these dislocations in HCP. Okay, so now we talked about AB type dislocation. Now, I will use those notation, and what is found is that even AB type of dislocation dissociate, and they dissociate into what? A sigma plus sigma B, and they end up with stacking fault, remember in the FCC. So, yes, here also we will get stacking fault. What is that type of stacking fault? Let us see if we can or how we can relate to the FCC type of stacking fault. So, remember in FCC we had ABC type plane, in HCP we have AB type plane. So, let us look at the AB type plane. So, if you write it down, the AB type plane should be like this. So, this will keep on going, but if you end up with any particular plane where you have this dissociation. So, in this particular case, let me say that you have a dislocation somewhere over here, or the dislocation glides such on this plane. So, these are our basal planes AB, all of these are basal planes, here one plane, another plane. So, one of these planes will have once the dislocation glides, this one part of this plane would have glided over the layer below it, and therefore, something will change. What changes? So, let us say this is the plane which does not, which remains as it is. Remains intact, and these are the, and this is the plane and everything above it then what will happen? This, because it has formed a partial dislocation. So, this much layer would remain as it is, and after that what you will see is that instead of this A layer will become C layer, B layer will become A layer, and therefore, you will end up with CA type of plane. So, this is the plane over which glide took place. So, after glide, this is the form of stacking fault that you would observe, and remember we are talking about these are your planes. If you look at it, these are your planes and your dislocation is like this. So, probably your edge dislocation extra half plane is somewhere like this, it is gliding, and therefore, in the glide when it is gliding, then it will create a stacking fault. So, everything above this, so this is the extra half plane region, everything in this side will change its position, and this is only happening when we are talking about the formation of partial dislocations. So, the A layer has become C and the B layer has become A after this partial, after glide and formation of partial dislocation. Okay, so, now let us come back to our this original equation which describes the formation of the partial dislocations A B plus sigma B, and it will be useful if we just go back quickly to look at what this means. So, here is this triangle A B has dissociated into A sigma and sigma B. So, this is what is happening, and I will show you again that this is exactly same. If you look only in this plane, it is exactly same as what we saw in FCC system. But for now, just based on that diagram and based on the Berger vector I have already described to you, you should be able to write down all the Berger vectors here. So, here it will become 1 1 bar 2 0 transforming to 1 by 3 1 0 bar 1 0. This is your A sigma, and sigma B will be 1 by 3. So, this is the perfect dislocation. If it had moved just that way, then there will be no change in the stacking fault, but since partial dislocation has formed, this is the kind of stacking fault you end up. And let us, now that we have written the equation, so why not calculate the energy, and you remember AB has energy of the type A square, A sigma has the energy of the type A square by 3. So, sigma B also A square by 3. So, when you sum it up, it becomes 2 by 3 A square. So, this is certainly lower energy, implies it is favorable to form. So, it is not that it will even energetically it is possible to form, it is not just theoretically what we have shown here. Here we are showing that energetically also this is feasible. So, it has lower energy, so it will tend to form. Now, talking about similarity to FCC. Where we had A by 2 1 bar 1 0 slip occurring on 1 1 1 plane. So, how is it similar? So, if we were to draw the plane atoms on this plane, so let us call it layer A, and we have another layer somewhere here, and it is, and I am intentionally drawing it a little bit smaller in size, although it will be of the same size and will be touching. This is just so that we can draw or clearly show how it is, how the transformation is taking place. So, this green layer is layer B. Now, if it were a perfect dislocation, what would have happened? This would have moved from over here to over here, but this is not what is happening, it is forming a partial. So, what is that partial? This is like this and over like this. So, your dislocation, which is this, which is given by the Berger vector A by 3 1 1 bar 2 0 breaks into two partials, and let me draw it more accurate, because like I said, this should be exactly same, and therefore, it should be a 30-degree angle. Okay. In the FCC also we get it at 30 degrees, here also we get it at 30 degrees, those partials, because you can see the plane is similar. At this level of plane, when you look at things, it will look exactly same. So, this will be your A by 3 So, these are your BP 2 and BP 1, and if they were moving apart, then this is how it would look like. So, this will be the region where you will have stacking fault created, and this will be your perfect crystal. This would also be your however, with even though with so much similarity, there is still something which is different over here in this when we are talking about HCP, and that is because layer A is a little bit different from layer B. So, now if we are talking about this, let us draw this again and assume that. So, in this particular case we assumed that the dislocation layer B glides over layer A. Okay. But in HCP, because all these planes A and B are not exactly same, we can have the other situation where you have okay. So, here what is different is we are saying that layer A glides over layer B. Therefore, your full dislocation is from here to here. So, full dislocation is still the same, but now the partials are actually like here. Okay. So, if I draw it, the partials are, so this is your A by 3 which means that this particular when you look at the BP1 and BP2, now their positions have interchanged. So, the Berger vector for the first one is this one and the second one is this one. So, this is something that is different when you have a HCP system. Here the layer B was gliding over layer A, and here layer A is gliding over layer B. Okay. So, before we close the chapter about the hexagonal systems, there are few points that I would like you to keep in mind. One of the first thing is how we said that basal slip and then the prismatic slip is what is preferred. So, overall basal plus prismatic, how many do we get slips, independent slip system? 4 independent slip systems. But if you look at the von Mises criterion, there should be at least 5 independent slip system. For homogeneous deformation of a polycrystalline material. Okay. So, it means that most of the time there are two implications, that for most of the HCP metals will not show homogeneous deformation at low temperatures, where only Bessel or prismatic is activated. And this is absolutely true, whether you are talking about even something like zirconium, titanium, magnesium, they do not show very good deformation behavior. They are not homogeneous at lower temperature. And even at higher temperature, some of these materials do show a very good homogeneous deformation. So, at higher temperature or at higher stresses, homogeneous deformation must take place due to. So, what are the possibilities that will lead to homogeneous deformation? So, there are two possibilities. One, that some of the other slip systems get activated. So, pyramidal or C+A system get activated. And there is still another possibility, twinning. So, we already have 4 slip systems, but twinning can act as a 5th independent slip system. So, twinning can lead to homogeneous, and both of these things have been observed. So, people have observed that this twinning does support homogeneous deformation, and in some cases there is a pyramidal slip or C+A type of deformation which leads to, which allows for a homogeneous deformation. And this one particularly is true for high stress and particular orientations. So, these are some of the important things about HCP. So, HCP is not a very, you can say, deformation friendly system. All the metals which fall in this category, they have to be modified in some way, sometimes higher temperature, or you change their C by A ratio so that other slip systems get activated and so on, and then you would be able to do or get good deformation behavior. So, even though they may have very good strength, ductility, etc., but some of these things can be missing, the homogeneous deformation can be missing, even machinability would be down, because the machinability is nothing but deformation at those conditions, and if the deformation is not good, so machinability may also be down, and then again one needs to make some modifications so that you can get good deformation behavior. So, we will end our lecture about HCP system here, and next we will talk about 2 more, you can say, more advanced systems. One in not an great length, but the most complicated, which is the ionic system, and another which is very important from a mechanical engineer's point of view and a materials engineer point of view, which is a super lattices, or which also give rise to systems super alloys. If you remember nickel super alloys, there are something called as super alloys. So, we will understand where do we get those behavior properties from when we understand the dislocations in super lattices. So, thank you, and we will see you in next module.